attending this session today. And I would also like to thank the organizers for inviting me to present to you. Today I'm going to talk about a study I have been developing with the help of Dr. Abdulrazak and Dr. H2Ri regarding the moisture monitoring of a railway embankment close to Edmonton. First, let me share some information about our site. It is located in Fort Saskatchewan, and the railway embankment foundation of the site is mostly composed of fine materials. It is about 50% of fine materials at the site, and we classified it as a clay subgrade. Due to the low permeability and the consequent water retention occurring at the subgrade, the track has undergone settlement and clay pumping, which led CP to tackle this problem by reconstructing the embankment and including two geotextiles, one in each layer interface, being a reinforcing geotextile, which is Mirafi RS580i, between the ballast and sub-ballast interface. And the other geotextile is the wicking geotextile Mirafi H2Ri. This geotextile was placed between the sub-ballast and the subgrade layers. And it is capable of removing water from the soil even in unsaturated conditions by the capillary effect. Since the impact of this wicking geotextile, which is currently used by CP to remediate other sites, since the impact of this geotextile, since the impact of this wicking geotextile, which is used by CP currently to solve problems like that, is not known, we decided to monitor its effect by inserting moisture sensors in two sections, one control section with no remediation done, and a remediated section of the track, one right beside the other. And while monitoring the moisture, we also monitored the daily precipitation and the meteorological data by collecting information from a weather station nearby. In order to make sure everyone would be safe while installing, in order to reach our goal and to make sure that everyone would be safe and the construction would take the least time possible, several meetings were done between the three parts involved, which were CP, UFA, and the contractor. After these meetings, it was decided that the construction would take about 2 days, and a total of 10 moisture sensors would be installed at the site. 5 would be in the remediated section and 5 in the control section. And this is how we divided the days of construction. On the first day, the track panel was removed and the embankment was excavated down to the subgrade, where 2 moisture sensors were installed in a trench. These sensors were installed at this moment because it would be necessary to cut through the geotextile to insert it at a later date, and we didn't want to damage the wicking properties of the geotextile. Therefore, it was better to install the 2 sensors of the subgrade before placing the geotextile. After installing the sensors and backfilling the trench that we digged for installing the sensors, the wicking geotextile was placed at the top of the subgrade. And after placing the geotextile, the sub-ballast was also placed, and it was followed by the installation of the reinforcing geotextile, the placement of the ballast, and then the reinstallation of the track panel. And this was the end of the first day. On the second day, while the crew reinforced another section of the railway, our team installed 10 access tubes in the embankment. 6 of them would go down to the sub-ballast, and the remaining 4 went down to the subgrade. Since the ballast is a very difficult material to go through, as mentioned by Dr. Hendry several times in our class, it was necessary to dig a trench through it, just as seen on the picture on the left. And then we had to install the pipes using an auger and a hammer at the same time, as you can see on the picture on the right here. So we dig the trench and then install the pipes using the auger and the hammer at the same time to go through the remaining layers, which would be the sub-ballast and the subgrade layers. So at the end of the second day, we had a total of 10 access pipes installed. 6 of them in the sub-ballast, and 4 of them went down to the subgrade. And 8 of these access pipes had 5T sensors installed in them. These sensors are capable of recording volumetric water content, temperature, and electrical conductivity data. And it was necessary to protect the wires of these sensors. So they were all protected by electrical shields, including the ones that were installed on the first day. They were also protected by electrical shields to avoid damages from tamping activities, from construction activities from the day before. Since these wires are very sensitive, it is very important to protect them, or else we could get mixed up data, or it could even not work anymore, because we have a lot of tamping activities around the track. To read the information from the sensors, we installed 2 data loggers at the site, one for the control and one for the remediated section. These data loggers were set up to collect data from the 5T sensors at 12-hour intervals. And whenever we installed these 2 data loggers, we saw that one of the sensors installed at the subgrade of the remediated section was not working. However, we couldn't reach it because, as mentioned, it was installed before placing the geotextile. We didn't have access to it. So unfortunately, we only had data from one sensor in the subgrade of the remediated section due to that. And there was nothing we could do about it. We couldn't replace the sensor. So this is the final setup of our site. And here you can see a blue pipe over here on the picture on the left. You can see a blue pipe at the shoulder of the track. And this blue pipe represents this D1 and DG1 that are on the right, figure. These pipes were used to collect moisture profile data using Diviner 2000, which collects the volumetric water content points at a 10 centimeter interval. So we would occasionally go to site and measure this moisture profile data and compare it to the 5T sensors that we had at the site. This figure is just to give you some perspective on the soils found at the site. And here you can see that while the ballast and sub-ballast has little to no fines, it is basically composed of granular material. The subgrade has about 50% of fines in its composition, and it is classified as a clay of low plasticity. So the data collections consisted of gathering the information stored by the data loggers, which, as mentioned, gather data at a 12-hour interval. And we also collected meteorological data from 3 different weather stations. However, we prioritized one weather station that is about 6 kilometers away from the site. We just used the other 2 for historical data. And in order to rule out the effects of ground freezing and snow accumulation, the period analyzed for this study went from July 23rd to November 8th of 2019. However, as you may remember, snow still occurred before this accumulation that happened after November 8th. So how did we consider that? You may be familiar with the concept of snow water equivalent, and it is defined by the equation shown here, and where HS is the snow depth and you may be familiar. You may be familiar with the concept of snow water equivalent defined by the equation shown, where HS is the snow depth. However, we had some challenges regarding the snow density represented at the top of this fraction here. As it changes with time, and to go to the site periodically to perform measurements would be time-consuming and costly for us. Then what we did is we decided to use a model to insert the snowfall into the analysis. And this model is also going to be used in the spring thaw analysis that is still going on for the site. So the snow density model we used is shown in this slide. I'm just going to go quickly talking about what you see here. This model considers the effect of time, climate, and local snow density. And it assumed that the density changes a little every day as some snow from the top melts and stay retained within the snow layer before penetrating the soil. For our site that is close to Fort Saskatchewan, we use the prairie parameters here for the densification and for the density factors, as shown in table 1. And this day of year here, it increases from October till July, and it is more explained in Storm et al. Paper. If you want to take a look at it, I can send to you guys. Now we have the total precipitation defined by the sum of the rainfall and the change in the snow water equivalent present on the top of the soil. Okay, so we have the precipitation and we have the moisture data figured out, but how can we relate these? There are several models that use land surface. However, they are too complicated and use use a lot of softwares, and it's very complex. However, we were able to find a correlation with a model that is called antecedent precipitation index. And the correlation of moisture and precipitation was done doing working with this model. And this model considers the precipitation of a number of days prior to the day analyzed, and it makes use of an attenuation coefficient here expressed by K. Over here we have K. This is an attenuation coefficient that is used to consider runoff, evaporation, and other things that may affect the moisture content of the soil. This coefficient is also responsible for lowering the importance of precipitation of days that are not the day analyzed, because we use a number of days before the day analyzed, and we consider that into our API for that day. And this attenuation coefficient works lowering the importance of the precipitation of the previous days by using this T over here. That in this case, T is the number of days prior to the day analyzed. So if I got the precipitation of a day that was 15 days ago from the day that I'm analyzing, this T will be equal to 15. So the attenuation coefficient will be way lower than it would be for the day we're analyzing, as T would be 1, and then the attenuation coefficient would be at its fullest value. The daily values for the model were also optimized by performing a curve fitting to visualize the effect of precipitation. And the best curve fitting found was the power regression. This was also found by other researchers to be a good relationship between the volumetric water coefficient, volumetric water content, that is found here on this side of the equation and the API. This seems to be a good optimization of the curve fitting of the volumetric water content with the antecedent precipitation index. Here are examples of the curve fittings used in this study. So here we see curves of the unchanged section, the control section. And the increase in moisture with higher precipitation index is visible for the sub-ballast, which is the one in the left here. So here you can see an increase in API and an increase in the volumetric water content. It's pretty visible that they go together. However, for the subgrade, which is here on the right, this relationship is not that strong. In this case, this is an odd relationship that we think may possibly be related to water retention occurring in this section. And I'll also explain the reason for thinking that this is due to water retention in the next slide. These curves are for the remediated section, and you can see that the relationship here has changed. And even with higher API values, the moisture does not change greatly. It changes. You can see a change, like it increases a bit, but it doesn't increase as much as we see in the control section here. So at the subgrade, we see a positive relationship, which is not seen for the control section, even though the moisture didn't change greatly. And this is the reason we think that the relationship of the control section may indicate water retention, because all the other sensors have shown positive relationships. Only the one at the control section showed this odd relationship. However, we'll be investigating more about it, and maybe a further analysis of the spring thaw may lead us to better conclusions regarding that. So these are the graphs we found using the curve-fitted API and the actual VWC, the volumetric water content. And the model seemed to predict well the moisture. So it was a good representation of the relationship between moisture and precipitation. Here you can see a difference in the moisture of both sections. While at the sub-ballast, the remediated section has shown a higher moisture content throughout the study. It also has shown less variation than the control section. And this is really interesting because even though we see a higher moisture content at the sub-ballast, it still seems to be less influenced by precipitation than the control section. And it is also interesting because at the subgrade, we see a constant moisture content at the control section and at the remediated section, even though the remediated section has shown to vary a bit more than the control section. And it has a 9% difference on moisture content. Here you can see about 26 overall, and here it's about 17 throughout the whole study. This has shown that the subgrade at the remediated section has a lower moisture content, even though it's a bit more responsive to precipitation, because the control section doesn't seem to be responsive to precipitation at this moment. But we need to confirm this trend, as it can be due to the reconstruction of the embankment rather than being the moisture management due to the wicking geotextile. So we'll be studying that this trend at a longer term analysis to confirm whether this difference is due to the moisture management of the wicking geotextile, or it's due the construction method or drying out of the soil while the construction was done. We need to confirm this using long-term analysis. Okay. So we also analyzed the effect of moisture in the strength of the subgrade by estimating soil water characteristic curves for the subgrade. These curves, the soil water characteristic curves, relate the volumetric water content to a suction value. And this suction value may lead to either a higher or a lower strength. This is basics from the unsaturated soils, soil mechanics. As suction increases, it is expected to have a higher shear strength rather than when you have a higher moisture content, you have lower suction. Therefore, this would lead to a lower shear strength. And here what you can see is a difference between this 9% difference seen here has caused the suction values going from about 700 for the control section to 3,000 for the remediated section. And this may imply that the remediated section might have a higher shear strength due to the higher suction seen for the section. In conclusion, we can see that the sub-ballast at the remediated section tends to be less sensitive to the antecedent precipitation, probably because of the moisture monitoring of the wicking geotextile, even though it has a higher moisture content than the sub-ballast of the control section. The subgrade of the remediated section, however, has shown to be more responsive to precipitation than the control section. And this might be due to water retention occurring at the control section. However, we still need to do a long-term analysis to confirm this trend. And also greater suction values at the remediated subgrade material may lead to a higher soil strength at the remediated site. If this trend is confirmed, that it's really good for our embankment. However, we still need to confirm that trend, and the analysis is being continued. I'm working on the analysis of the spring thaw right now, and we'll be able to determine the long-term effects of including this geotextile in the railway embankment. Now I would like to thank NSERC, Canadian Pacific and Canadian National Railway for sponsoring this research. I would also like to thank Kelvin Sattler, which is he's the guy that helped us with our data loggers, because our data loggers are handmade. They were not bought. They were made by Kelvin. I would also like to thank our graduate students that helped with the site instrumentation, which are Jorge, Daniel, Kevin, Evan, Areza, and Adam. They have also helped a lot taking us to the site because we were not able to go by ourselves. I would also like to thank Danny and Adam and Troy to helping us to get access to our site. They were supervisors of our track. And now I'll be happy to take any questions you might have. And once again, thank you for being here today. And thank you everyone for taking your time to be here with me.
All right, thanks Camila. We kind of jumped the gun and skipped the introduction, so maybe I'll just jump on that right now for Camila. So Camila's got a bachelor's degree in civil engineering at, I'll do my best here, at Universidade Federal de Viçosa in Brazil, where she found out she was passionate about soil mechanics, soil improvement, and site instrumentation. She is currently a Master's of Science student here at the University of Alberta in the Geotechnical department, working under the supervision of Dr. Michael Hendry. Her master's work is focused on conducting research about the railway reinforcement monitoring, as we just saw here. So just to kind of remind everyone, so any questions we'll do through the chat box, just to make sure that we have kind of a consistency with how we're asking the questions, and then we don't have people kind of having run along questions that tend to eat up a lot of time. And otherwise, that's pretty much it for housekeeping things. We are uploading videos to a YouTube page that we created last week, where we'll have all the presentations upkept there. So if you ever want to watch or rewatch something again, then you'll be able to go on there and find it. I'm sure that Vivian will send it out one or two more times over the semester. So I'll pass off to Lang here. I don't know, I haven't seen any questions in the chat box yet, but if people have questions, please throw them in the chat, and we'll have Camila answer those for them.
Thank you, Kevin. Yes, just as Kevin mentioned that it would be much more organized and fair to other students if you can put your question just in the chat. And here I can see one question from Fernanda. It is, did you use one reading per day or an average of the 2 readings per day about the moisture measurement? Can you answer this question, Camila?
Yeah, I can answer this question. What happened is that some days we had higher amounts of precipitation and we had a great change in the moisture. It would go from 3% to 7%. So we decided to do an average of the 2 readings of the day to make sure to account for that precipitation.
Thank you.
Yeah, I would also add some information at the chat box because I have a paper on GeoVirtual that is basically what this presentation is about. So I'll just send this paper and also one paper detailing the snow water equivalent method that I used, because I know it's hard to keep up with all the information at once. So I'll just send these information if anyone wants to know more about it.
That would be great. So please just share the paper with us in the chat and we can follow up with you. I also saw one question from Kevin. How long or how many readings do you think it is required to definitely say that the geotextile is working? Sorry, Camila.
Sorry, I'm on mute. So you were thinking that probably 1 year to 1.5 years would be good. But I know that ProISA has a plan to at least read it for 5 years to make sure that in a longer term analysis, it would be working.
Good. Now I don't see any other question coming up right now, but oh, sorry, there's one more. It's from Steve. When you're fitting API, you had one of your R-square very low. Does that affect the predictability of your relationship?
So as shown in the graph, it didn't affect that much the predictability. However, we are just waiting for more readings. I think it was not enough readings for the model to be certain, like to be really correct. Now that I'm working on the spring thaw analysis, I'm seeing higher R-squares than what is seen for these information that I have here on the presentation. Now I have an R-square close to 60, 0.6. I know that in this paper, I had one that was close to 0.3, but since the moisture didn't change much at the subgrade, the predictability was not affected by that. For the sub-ballast that I had a higher permeability and I had a lot of changes, I had a good R-square, so it didn't affect the predictability at all for the sub-ballast. And for the subgrade, it didn't affect because it didn't change that much during the time of the study.
Okay, thank you for your explanation. I'm wondering if anyone still have a question. If not, I think, thank you for your presentation, Camila. That was nice work. And also, thank you for everyone who are attending this seminar. And before the meeting is adjourned, I just wondering, do we have any other announcements?
I don't think we have any announcements, so just come back next Wednesday. Actually, Lang will be the one presenting to us, so we'll look forward to that. And thanks everyone for coming up to this presentation.